Alright, so when we look at delta H in reactions, there's sort of three simple rules to remember. Okay, there's sort of a fourth, which is just that you have to be very, very careful about your gas and liquid and solid, the state of the actual molecules, because if the state is different, gas going to solid is not the same as the liquid going to the solid. So you have to be very careful about that you're not changing and that things match up. Okay, so let's take a look at an example of this. So the first one, let's look at water, solid, the ice form, going to liquid water. So we're melting ice. Really exciting reaction here. This has a delta H associated with it. Okay, that delta H is equal to 6.01 kilojoules per mole. Now, taking a look at this, what it means is, if we look at the first one, we reverse the reaction, you flip the sign of delta H. Pretty simple. Therefore, H2O liquid going to H2O solid, so freezing water. The delta H is going to be equal to negative 6.01 kilojoules per mole. And if we need to multiply by a coefficient, so if I want to know how many it was for 2 moles of H2O liquid going to 2 moles of H2O solid, well, since the delta H is per mole essentially, it's now negative 12.01 kilojoules per mole. 12.02 actually, but with sig figs, I guess we would actually call it 12.0. We'll just do that for now. So when delta H is in units per mole, the mole refers to the coefficient of whatever molecule you're working with. So if you look right here, this is still written as kilojoules per mole, even though it's now for 2 and for 2. So it's essentially saying the same thing. You would write this out as negative 12.02 kilojoules per 2 moles of H2O liquid. The one above it you would write as negative 6.01 kilojoules per 1 mole of H2O liquid. So in either case you have the same situation going on. Okay, so let's do an example problem with the stoichiometry. Alright, so let's now look at this problem here. We have a reaction of hydrogen gas and oxygen gas to make water vapor, and we're given a delta H. We want to know how much heat was released by this reaction. If I collected 500 mils of water vapor at 400 degrees Celsius and 1 atmosphere pressure at the end of the reaction. So we have a gas law problem here. Okay, the first thing we have to do is we have to write out this reaction. So we have 1 mole of H2 gas. It's reacting with oxygen gas to make water vapor. Okay, if we take a look at this, we've got 1 oxygen over here. We've got 2 over here, so in order to balance this and keep it as 1 H2 as requested, we would have to make it 1/2 O2. And the delta H of this reaction is negative 285.8. That's kilojoules per mole as written. So remember that's all sort of relative. It's that many kilojoules for 1 mole of H2, or 1 mole of H2O because it's written that way, but it's negative 285.8 kilojoules per 1/2 mole of oxygen. Alright, so now we have to figure out how much we actually reacted to figure out how much heat we actually evolved here, how much heat we lost as part of this reaction. So the first thing we're going to do is our gas law, N equals PV over RT. And we're given a pressure, 1 atmosphere, just going to leave some of the digits off, a volume, 0.5 liters. Okay, you need to carry through 3 sig figs, but we're going to not worry about that right now. And 673 Kelvin. Okay, 400 plus 273. Alright, so we do that out, and we're going to get 0.00905 moles of water. Okay, so I now know how many moles of water vapor I have. Now what I need to do is apply that to the delta H to find out how much heat was actually released by this reaction. So I take 0.00905 moles of H2O. Okay, I guess we should specify that that's the gas. And we know from this reaction that there's negative 285.8 kilojoules per 1 mole of H2O gas. Multiply that out, you get negative 0.259, sorry, negative 2.59. Correct that. Negative 2.59 kilojoules. So that right there is going to be your answer. That tells you that even though this reaction with 1 mole would do negative 285.8, given what we had, this is how much heat was actually evolved. Okay, in later problems we're going to figure out what to be able to do with this, measure how much temperature change there might be to a vat of water as a result of this reaction, or how much it heated up metal around it, or anything sort of along those lines. So there's a lot of different things we can do with that. But here's an example of a pretty straightforward one. Okay, the only thing you really need to look out for is right here. This is 1 mole of H2O, just because in this case it's 1 mole of H2O. If this reaction was doubled, if we had 2H2 plus O2 gas goes to 2H2O, the delta H would have to be doubled as well. Okay, it'd be negative 570. And then you would have to write it as negative 570 kilojoules divided by 2 moles of H2O. Okay, so you can do it either way, you just need to be careful about what you put for those moles.